Good afternoon to all. This is Uma Shankar, working as a lecturer in AC at Government Polytechnic College, Kosi. So today I am dealing with the subject Advanced Engineering Mathematics for Electrical Engineering students in 4th semester. So today my topic is on inverse Laplace transforms. In this, I'm going to discuss about multiplication and division by powers of S. So in the last class, we have completed about the definition of inverse Laplace transform, and also we have seen the linearity property of a given Laplace transform, and also some uh, basic elementary functions, how you are going to apply the inverse Laplace transform to the given functions. And next we have completed about the first shifting theorem by using the inverse Laplace transform. In this class, we are going to explain about only how to perform the multiplication by powers of S and division by powers of S using the inverse Laplace transform. So first I will give the theorem statement or definition of your multiplication by powers of S, and then we will go into the problem how you are going to do the problems on this multiplication by S method. Okay, right. So in this multiplication by S method, so if you see that, so if Laplace inverse of f of s is equal to f of t, so in this inverse Laplace transform, shortly denoted as ILT. So here we are converting from S domain to T domain in the inverse Laplace transform. So that's why we are taking a Laplace inverse of f of s is equal to f of t, and f of 0 is equal to 0. That is nothing but initial conditions. So initial conditions, to consider the initial conditions, these are all initial conditions are 0. F of 0 is equal to 0, or f dash 0 is equal to 0, f double dash 0 is equal to 0. So these are all initial conditions with respect to this function. Okay, right. So, and in this case, f of 0 is equal to 0 initially, then Laplace inverse of s into f of s. Okay, if s is, that is multiplication by powers of s. So when s is multiplied with f of s function, then that is equal to f dash t. That is nothing but you have to make the first time derivative, that is first derivative to the f of t function. Okay, here f of s should be converted in terms of f of t. Okay, if it is multiplied by s, then you have to do the one time derivation. Okay, or differentiation with respect to t for the given function. Okay, that is nothing but whatever the function which is converted by using from f of s. F of s is converted to f of t. Okay, this is about your multiplication by powers of s method. Simply Laplace inverse of s into f of s is equal to f dash t, that is equal to d by dt of f of t. Okay, right. So already we have done this theorem statement in Laplace transform. So here I will explain you in a simple way. So from the Laplace transform of derivatives, okay, we have a Laplace transform f dash t is equal to s into f of s minus f of 0. So here clearly mentioned in the definition or in the theorem statement only, f of 0 is equal to 0. All the initial statements are is equal to 0. That's why to put f of 0 is equal to 0. So put f of is equal to 0. F of 0 is equal to 0. Then we'll have only s into f of s here. Okay, right. So from this, if you apply the inverse Laplace transform on both sides, then what you will get? F dash t is equal to Laplace inverse of s into f of s. So Laplace inverse of s into f of s is nothing but your f dash t. Okay. So this is about how you have got this. This is the proof of your theorem statement. Okay, and the theorem which we are going to be proved. Okay, right. So this is for when s is multiplied with f of s function. Okay, s power 1. This is just you have to assume that this is s power 1. If you go for s power 2, then what you will write here? So Laplace inverse of, if it is s square into f of s. If f of s is multiplied by s square, then s square into f of s can be represented. So you have to do the 2 times differentiation. d square by dt square into f of t. Or simply it is represented as f double dash of t. So this is the short notation. Or instead of this, you can use this notation also, d square by dt square into f of t. So in general, it can be represented. It can be representation for nth for a nth power, for nth power of s. Okay, that Laplace inverse of s power n into f of s is equal to f power n into t. That is nothing but you have to differentiate the f of t with respect to n times. Okay, so d power n by dt power n into f of t. Okay, for all this case, so the initial conditions are is equal to 0. That is f of 0 is equal to f dash 0 is equal to f double dash 0 is equal to so on up to for nth function, up to the nth function n minus 1 function, the value will be is equal to 0. Initial condition value will be is equal to 0. So this is your theorem statement and the proof of this theorem. Okay, so you have to remember this. So when f of s function is multiplied by s, then simply you have to convert this f of s into f of t and do the differentiation. Either you have to do the differentiation either one time or two time depending upon the s power. Okay, depending upon the s value. That is, if you have the s, then you have to do one time derivative differentiation. If you have the s squared, two times derivation, 3 s cube, then you have to perform the 3 times differentiation. Okay, now we will see a problem on this multiplication by powers of s method. Okay. So Laplace inverse of s by 4s square minus 25. Okay, now this is your f of s function. Why? Because here it is represented in terms of s domain. Okay, so Laplace inverse of f of s. Laplace inverse of f of s. F of s is equal to s by 4s square minus 25. So you cannot use this one. You cannot use this. Yes, why? Because so this can be separated as s into f of s. This can be divided in this way, s into f of s. From this Laplace inverse of s into what is f of s? That is nothing but 1 by 4s square minus 25 minus Laplace inverse of s into 1 by 4s square minus 25. And this can be your f of s. Okay, this can be your f of s. Okay, right. So from this, apply Laplace inverse on both sides. Laplace inverse of f of s equal Laplace inverse of 1 by 4s square minus 25. So here we'll have the always this s square coefficient should be 1. So here we'll have the 4. That's why you have to take 4 as a common here. So if you take 4 common, then what will get 4 into s square minus 25 by 4. Okay. Now this can be converted as 4 into s square minus, so 25 by 4 can be written as 5 by 2 whole square. Okay. So now this equation can be equal to, it can be compared with Laplace inverse of 1 by s square minus a square. Okay, 1 by s square minus a square, that is given as sine h at by a. That is sine h at by a. Here a value is equal to 5 by 2. Okay, right. So this that previous equation is compared with this formula. Okay, in that formula, so in place of a we'll have the 5 by 2. So in place of a, wherever you will have the a, simply you have to substitute as a 5 by 2. Okay. So we'll have a 1 by 4 in the denominator, that is 4 in the denominator, 1 by 4 into, okay, so 1 by a value is 5 by 2, sine h 5 by 2 into t. Okay, right. So from this, if you simplify this one, 1 by 4 into, so this 1 by 5 by 2 can be written as 2 by 5. So from this 2 1 the 2, from this 1 by 10. So this is your value. So this simplification part is equal to your 1 by 10. And sine h 5 by 2 into t, sine h 5 by 2 into t. Okay. So now this, so we are not using any initial function here. So simply that value should be is equal to 0. Okay, he has not mentioned any initial value. Simply you have to defaultly take this value as a 0 only. Okay, right. F of 0 is equal to 0. So from that, so now this will be your f of t function. So now you have converted this f of s function by applying the Laplace inverse, and this can be converted into f of t. Now use this theorem, that is by using multiplication by powers of s method. Okay, you can apply this. You can apply this theorem, okay, or method. So you got this f of t. So by using this method, okay, Laplace inverse of s by 4s square minus 25 can be written as, that is equal to Laplace inverse of s into f of s. So it is of the form s into f of s. When you are converting this one into s into f of s, then it can be written as f dash into t. Why? Because this f of s is multiplied by only s term, s power 1. So yes, if it is s power 1, you have to differentiate only one time with respect to this f of t function. So we got this f of t is equal to 1 by 10 sine h 5 by 2 into t. Okay, so you have to differentiate this f of t with respect to one time. So that's why this Laplace inverse s by 4 s square minus 25 is equal to f dash t. Okay, what is f of t? That is nothing but this one. F dash is nothing but you have to differentiate this function. Okay, 1 by t, 1 by 10 sine h 5 by 2 into t. Okay, so differentiate this one. So 1 by 10 is a constant, it should be taken outside. It should be taken outside 1 by 10 into differentiation of sine h 80. Okay, so if you take the differentiation of sine h 80, differentiation of sine h 80. So what is the differentiation of sine h 80? It is nothing but cos h 80 into the t coefficient value. What is the t coefficient value? A. So here a value is equal to 5 by 2. So cos h 80 into a. Okay. So a value is 5 by 2. That's why you have written this 5 by 2. So if you simplify this one, 1 by 10 into 5 by 2. So 1 by 10 into 5 by 2 is nothing but 1 by 10 into 5 by 2. 5 1 the 5 2 is so it is nothing but 1 by 4. Finally, we get 1 by 4 into cos h 5 by 2 into t. So this is the way you have to simplify the multiplication by powers of s method. Okay, right. So now we'll see the one more problem on this. So whatever the problems I have covered here, whatever the problems I am going to cover in this session. So these are very, very important, and all these methods are, all these examples are different. Okay, so method will be the same, but the approachment in one example with respect to another example is somewhat little bit different. Okay, so you have to understand how one method, one example is different with respect to another example when a function is given. Okay, right. So if you go for the second problem, find Laplace inverse of s by s plus 2 whole square plus 4. So this can be compared with Laplace inverse of s into f of s. This can be compared with Laplace inverse of s into f of s. Okay, right. So Laplace inverse of s into f of s is nothing. So now from this, Laplace inverse of s into 1 by s plus 2 whole square plus 4. Now the f of s will be this function 1 by s plus 2 whole square plus 4. That, sorry, so here it is s plus 2 whole square plus 4 f of s. Mistake. Okay, 1 by s plus 2 whole square plus 4. Okay, right. Change this one. Okay, right. So here f of s function will be 1 by s plus 2 whole square plus 4. Okay. So applying Laplace inverse on both sides, Laplace inverse of f of s is equal to Laplace inverse of this entire function. So if you see carefully in the denominator, so it is s plus 2 whole square. Okay, s plus 2 whole square plus 4. Now this function is first shifted. Okay, this is a shifted version. Okay, this is a shifting method. So that's why we are by applying the first shifting theorem. Now this has to be simplified first. Why? Because either in the denominator should be always, it can be s minus a or s plus a type, or it can be 1 by s square plus a square, or s square minus a square, or s by s square plus or minus a square. So you have to always remember the function in the denominator should be of these types. Okay, but when you see here, it is s plus 2 whole square. That is nothing but, so it is shifted by some value. So that's why we have to apply the first shifting theorem in order to simplify this. So when you will apply this first shifting theorem, what you will get? So it is shifted by plus 2 times. That is nothing but So if you apply this theorem, then what you will get is nothing but this plus 2 will be eliminated and it can be written as e power minus 2t. So already we have done this first shifting theorem problem. Just you can verify the first shifting theorem how you are going to apply. That is nothing but simply Laplace inverse of 1 by s plus a whole square, 1 by s plus a whole square plus b square. So if it is of this type, that is equal to, so it can be written as e power minus at into Laplace inverse of 1 by s square plus b square. 1 by s square plus b square. Okay, this is the equation. So plus at can be written as e power minus at by using this first shifting theorem. So in place of a, we'll have the 2 e power minus 2t into Laplace inverse of. So this plus 2 can be eliminated and you will get it as a s square plus 2 square. 4 value is nothing but 2 square. Okay. So from this, f of t is equal to e power minus 2t. So Laplace inverse of f of s is nothing but f of t. So by applying this first shifting theorem, we'll get e power minus 2t into Laplace inverse of 1 by s square plus 2 square. So if you see carefully in the denominator, that is 1 by s square plus a square. Now this can be written as 1 by a sine 8. 1 by a sine 8. What is the a value here? 2. So 1 by 2 sine 2t. So that is represented here. Okay. Right. So finally, what is your f of t? So f of t will be is equal to. So the f of t value will be is equal to. F of t is equal to, this is your f of t. That is e power minus 2t sine 2t by 2. This is your f of t function. Okay, now we have to apply this multiplication by powers of s method. Okay, right. So Laplace inverse of s by s plus 2 whole square plus 4 is equal to Laplace inverse of s into f of s. That is nothing but your f dash t. Okay, s into f of s. Now we have converted this f of s function into your f of t. So by using this multiplication by s method, so then this can be written as f dash t. So it is multiplied by only s term. So that's why only you have to do the one-time differentiation. Okay, from that d by dt of f of t. What is f of t? E power minus 2t into sine 2t by 2. Okay, right. So now here we'll have the two functions. In differentiation, you will have the two functions. That is, it is considered as a u function, and this one will be considered as a v function. These two will be a constant, it can be taken outside. So we have to differentiate these two functions by applying the product rule or differentiation of UV rule, multiplication. That is nothing but product rule, UV rule. So I have written that one here. Okay. So we'll apply the UV rule, then d by dx of UV. That is, it put the u as a constant and differentiate with respect to v, and plus next to v as a constant, differentiate with respect to u. Okay, right. So in that way, you have to apply this differentiation by applying the product rule. So 1 by 2 is a constant, the denominator term is constant, 1 by 2 into the first two. U is a constant, so e power minus 2t into differentiation of v term. V is nothing but sine 2t. So if you differentiate this sine 2t, what you will get? Cos 2t into 2. Okay, t coefficient is 2. That's why 2 cos 2t plus. Okay, plus. Next to v is a constant. V is nothing but your sine 2t. Next to differentiation with respect to u. So differentiation of e power minus at. That is nothing but e power minus at into t coefficient is minus 2. That is minus 2 into e power minus 2t. This is the way you have to apply this product rule or differentiation of uv rule. Okay. It is not u by v, it is uv rule, product rule. Okay, right. So if you simplify this one, then what you will get finally? So 1 by 2 into 1 by 2 into this is 2 e power minus 2t cos 2t. Okay. So in this, if you simplify plus into minus 2 sine 2 e power minus 2t into sine 2t. So in this, you will have the 2. Here also you will have the 2. And if you take the 2 common in both the functions, then finally this 2 and the common term of these two functions 2 will get cancelled. Finally, you will get e power minus 2t cos 2t minus e power minus 2t sin 2t. So in both the cases, you will have the e power minus 2t as common, so which is represented here, e power minus 2t into cos 2t minus sin 2t. So this is the way you have to solve the problem. Okay, right. So this is the one method. So this is the first example approachment, and the second example approachment is somewhat little bit different. Okay, so if you go for the third case, in third case, if you observe that, so we'll have the s square, Laplace inverse of s square by s minus 3 whole square. Okay, right. So now from this can be compared with respect to Laplace inverse of, again, so it is s square now, so that's why s square into f of s. I'll write this one as s square into f of s. Laplace inverse of s square into f of s can be written as s minus 3 whole square. Now this f of s is nothing but 1 minus 3, 1 by s minus 3 whole square. Okay, all right. So again in this, we will have a 1 by s minus 3 whole square. So again you are going to apply the first shifting theorem. Okay, after applying the Laplace inverse on both sides. Okay, then I have to apply the first shifting theorem. So you can do in any way this problem. This problem can be simplified in any way, but it's better to apply the first shifting theorem. So Laplace inverse of f of s is nothing but f of t, that is equal to. So we'll apply the reverse, it is inverse Laplace transform by using the first shifting theorem. So it is shifted by 3 times. It is minus 3 times. That is represented as e power 3t. Previously it is plus 2 times. Okay, plus 2 is nothing but Laplace inverse of 1 by s plus a whole square. We'll apply the inverse Laplace transform using the first shifting theorem, that is e power minus at into Laplace inverse of 1 by s square. This is, so if you have the minus here, then it can be represented as e power at into Laplace inverse of 1 by s square here. So this is the equation. So e power 3 into Laplace inverse of 1 by s square. So what is Laplace inverse of 1 by s square? So Laplace inverse of 1 by s square, the formula for this is nothing but s power n, that is equal to t power n minus 1 by n minus 1 factorial. What is n value here? 2. So 2 minus 1 by 2 minus 1 factorial. T power 1 by 1 factorial. That is nothing but t. So e power 3t into t. Okay, right. So for all this, again, the initial conditions are 0 here. Clearly f of 0 is equal to 0, f dash 0 is equal to 0, f double dash 0 is equal to 0 for all the cases. So if he has given in the problem, then you can applicable here. So if he has not given in the problem, then you can leave it. Okay, all right. The Laplace inverse of s square by s minus a whole square, that you have to find out. So from this Laplace inverse of s square into f of s. Now this f of s, by applying the Laplace inverse to this f of s, we got this f of t. So it is multiplied by s square. That's why you have to do 2 times differentiation to this f of t function. Okay. So d square by dt square is equal to, sometimes this can be also written as f double dash of t. Either this way or this way, both are same. So d square by dt square into f of t. What is f of t? T into e power 3t. We got this f of t as 3 into e power 3t. Okay. So d square by dt square equal to t into e power 3t. Okay. So first what we have to do? So we have to do the one-time differentiation to this t into e power 3t. That is d by dt into d by dt of t into e power 3t. Again, here we'll have the two functions u and next one is v. So what we have to do? So again, you are applying the differentiation of uv rule, that is applying product rule, d by dx of uv rule again. So here u will be the t value, v will be the e power 3t. Whichever you can consider that t can be v function and e power 3t can be root function. So it is, here we don't have the any Eilert procedure, so you can assume any function as a u and any function as a v function. Okay, any term as a v function. Okay, right. So if you use this one, then first v u is a constant and differentiate this one, you will get it as a 3 into e power 3t plus. Okay. Next is v is a constant, v is e power 3t into differentiation of u. That is nothing but differentiation of t is nothing but 1. So what you will get here? So from this d by dt. So d by dt into. So it is only the first differentiation value. So get it as a e power 3t as common here in both the cases. Here you will have a e power 3t, here also you will have a e power 3t. Left out term in this is 3t, and this left out term is 1. So plus 1. So this is the function. Okay. So by applying the first differentiation, we will get that term. So that is represented. So to see this one, that you got that term here. So again, what we have to do? So we have to again do the second time differentiation. So d by dt of e power 3t into 1 plus 3t. So assume this as a u function. Again, this one will be the v function. Okay, right. So if you consider that, if you apply that, okay. So in this case, this can will be the v and this can will be the u function. Sorry. And this one will be the u and this one will be the v, whatever it means. So keep u as a constant e power 3t into. So differentiation of this 1 plus 3t. So differentiation of 1 is 0 plus differentiation of 3 into t. 3 is a constant. Differentiation of t is nothing but 1. So 0 plus 3 into 1 is nothing but 3. So we get 3 here. Plus. Next, v is a constant. 1 plus 3t. Differentiation of e power 3t. Differentiation of e power 3t is nothing but 3 e power 3t. So after simplifying of this equation, that is, so this term will be used as 3 e power 3t plus, and this one will be the 1 plus 3 t into 3 e power 3t. In both the cases, 3 e power 3t, 3 e power 3t is present. So that's why 3 e power 3t as take as common. So if you take 3 e power 3t as common, so the first term you will get as 1 plus remaining term in the second will be 1 plus 3. So 1 plus 1 is nothing but 2. 2 plus 3 into 3 4 3. So that is the final answer. Okay. So this is the way you have to solve the problem on multiplication by p power n method. Sorry, s power n method. It is in yes, no? So that's why you have to simplify the problems by using this method in this way. Okay, right. So next we'll go for the division by powers of s method. Okay, so we have seen previously multiplication by powers of s method. Now we will see the division by powers of s method. Again, the theorem statement or proof theorem statement or method can be given as, again, Laplace inverse of f of s is equal to f of t, and then Laplace inverse of f of s by s, because it is a division by powers of s method. So that's why Laplace inverse of f of s by s division by s is equal to integration 0 to t f of u into du. So this is your theorem statement. Okay, this is your theorem statement. So if you have 1 s in the denominator, then you have to do one time integration. Okay. So if you have the one more s term, that is nothing but s square, then what you have to do? So you have to do the 2 times integration 0 to t, integration 0 to t, again integration 0 to t f of u du into du. You have to do 2 times integration with respect to u. Okay, right. So in general, if you have the n power, that is nothing but if you have the nth power, then you have to do the n times integration with respect to 0 to t. Okay, you have to apply this integral from 0, lower limit is 0, upper limit is t. So you have to perform n times integration. Okay, right. So this is about your division by powers of s method. So this is the basic formula. This is your generalized formula for the s power n. Okay, division by s power n method. Okay, right. Now we'll see a problem on this. Okay, right. So previously, if you see that, we'll have a Laplace inverse or something like s by s square plus a square term. It is multiplication part. So s into something 1 by s square plus a square. Now we'll have the system will be present in the denominator, that it is can be represented as Laplace inverse of 1 by s into 1 by s square plus a square. So you have to divide into the two functions. Now this can be written as Laplace inverse of. So this entire term can be represented as f of s by This is a denominator function, that is nothing but s. So this entire term can be represented as a f of s and into 1 by s, that is nothing but f of s by s. Now we have to convert this f of s into f of t. Then we have to apply this theorem, that is nothing but division by power of s method. Okay, right. So from this we got that f of s can be written as Laplace inverse of f of s can be written 1 by s square plus a square. So it is directly represented as a formula 1 by a sin a t, that is nothing but your f of t. So by applying the inverse Laplace transform of division by powers of s method. So simply you have to apply the inverse Laplace transform by using the division by powers of s method. Laplace inverse of 1 by s into s square plus a square equals Laplace inverse of 1 by s into 1 by s square plus a square. That is nothing but division by s method. Okay, division by s method. So if you do this division by s method, you have to do the one time integration. That is g integral 0 to t f of u into du. So it is given as here integral 0 to t f of u into du. So what is f of u here? F of u is nothing but your f of t only. So here we are using the t variable, here we are using the u variable. So here the variable can be interchanged, but the function representation will be same. Wherever you have the t, you can simply apply the u here. Why? Because so here the integration is varied with respect to t. Okay, it is varying from 0 to t. So that's why we are changing. We are using the different variable in order to represent this function. Okay, right. So in place of f of u, you have to substitute as 1 by a sin au. In place of t, you have to substitute as u. Okay, 1 by a sin au into du. It is differentiate with respect to u. Sorry, integrate with respect to u. Okay, right. So if you see here, so 1 by a is a constant which can be kept outside. So now we'll have it 1 by a if we kept outside, integration 0 to t sin au into du. What is integration sign? Can be represented as integration sign can be represented minus cos au by u coefficient is a. So 0 to t. It is integrating with respect to u. That's why what you have to do. So integration of sin au can be written minus cos au by a. Here u coefficient is a. So that's why it will get into the denominator. If it is differentiation, it will get into the, it is multiplied to the numerator. So it is integration. That's why it is divided into the denominator. Okay, you can take into the denominator. Right. So limits are from 0 to t. Okay, limits are from 0 to t. So apply this upper and lower limit to this function. That is nothing but wherever you will have the u, simply you have to apply this upper limit and the lower limit. Okay. So this a will be taken outside. So you will get it as a 1 by a square, and this minus term will be also taken outside, minus 1 by a square. So from that, if you substitute the upper limit, what you will get? Cos a into t, cos a t minus. If you substitute the lower limit in u, that is cos a into 0, that is nothing but cos 0. What is cos 0 value? 1. Okay. So you get cos a t minus 1. So if you multiply this minus term internally, then these two terms will get interchanged. Okay, so from that you will get it as a 1 minus cos at by a square. So this is the final value of Laplace inverse of 1 by s into s square plus a square. So that in the question he has asked that show that this function is equal to 1 minus cos at by a square. So that one we have proved. Okay, this is the way you have to solve the problem using the division by powers of s method. Okay, now we will see the one more problem in this Laplace inverse of, okay, 1 by s into s square plus 2s plus 2. So again this one can be compared with Laplace inverse of 1 by s into 1 by s square plus 2s plus 2. Okay, now this entire function can be represented as, this entire function can be considered as a f of s by this s. So center function can be considered as f of s into 1 by s. That is nothing but f of s by s. Now you have to convert this f of s into f of t. Okay, f of s into f of t. Laplace inverse of this function is nothing but your f of s. So now this can be simplified as, this is a quadratic equation. Now this can be simplified as like this. So already we did these problems in the first shifting theorem. Once again I am explaining you. S square plus 2s plus 2 can be written as this can be written as how we are going to write this one, a square plus 2 into a. So 2 into a value is s. What is the b value? What value you have to substitute here in order to get this 2s? That is nothing but 1. So if you substitute 1 here, that is if you put 1 here, then 2 into s into 1 is nothing but 2s. So you get this 2s, b value. Okay, you get this 2s value. So s square plus 2ab plus, so we don't have the b value, that's why we have to add the b value and we have to subtract the b value. B square minus b square plus, you will have the here plus 2 term. So plus 2. So this entire equation a square plus 2ab plus b square can be written as a plus b whole square. A plus b whole square. Next, this one is minus 1 plus 2. So it's plus 1 whole square. Minus 1 plus 2 can be minus 1 plus 2 is nothing but this value is plus 1. So this is the way you got this equation. Okay, right. Again, by using the first shifting theorem, it is shifted by plus 1 here. So again, you are going to apply this first shifting theorem. What you will get? E power minus 1 into t. So that is represented as e power minus t into Laplace inverse of, you will get it as a s square. So this plus 1 can be represented as e power minus t. You will get 1 by s square plus 1 square or 1, whatever it may be. Okay. Now, Laplace inverse of 1 by s square plus 1 or 1 square. So the basic formula for this is nothing but 1 by a sine a. So what is a value here? A value is 1. So 1 by 1, that is nothing but 1. Sine a value is 1. So you get it as a sine t. So the simplification of this will be sine t multiplied by e power minus t. So finally, you will get f of t is e power minus t into sine t. Okay. So that is represented here. After simplifying of this, you get e power minus t into sine t. That is your f of t. So now what we have to do? So you have to apply the inverse Laplace transform using this division by powers of s method. Okay. So Laplace inverse of this entire function is given as Laplace inverse of f of s by s. That is equal to 0 to t f of u into f of u du. Okay. So 0 to t. What is f of u? F of u is nothing but your f of t only. So only we are changing the variable here. So f of u. Okay, f of u is equal to e power minus u into sine u. Okay, e power minus u into sine u into du. Okay. So now this function will have a formula, that is nothing but by using the formula e power integration e power ax into sine bx dx. Okay, so this equation or this entire integration term, which is same as integration e power x into sine bx into dx. So for this you will have a formula e power x by a square plus b square into a sine bx minus b cos bx. From this, if you compare this formula with respect to this, to compare this entire equation with respect to this formula, what will it? Here a is equal to minus 1. So we use this a value is equal to minus 1. Okay, and next b value is equal to 1. So here b value is 1. So you see that b value, so b value is equal to 1. Okay, so if you substitute a is equal to minus 1 in this, b value is equal to 1, you get it as a e power minus u by minus 1 square plus 1 square into, so a value is minus 1, b value is 1, that's why sine u minus 1 into cos u. So where integral varies from 0 to t. So it is just for integration e power x sine x, but here we'll have the limits value, that is it will vary from 0 to t. So we'll apply this 0 to t. Okay, right. So now after simplifying of that, so finally we'll get Laplace inverse of 1 by s square plus 2s plus 2 is given as e power minus u by 1 plus 1 into minus sine u minus cos u. Here this integral will be varies from 0 to t. Now you have to apply this upper limit and lower limit in this function. So here by 2. So here in the denominator 2 is a constant which can be taken outside. So in both these terms you will have the minus. Okay, that's why you have to take this minus term as common. So that also keep outside, that is minus 1 by 2 into e power minus u sine u plus cos u. Okay, so now apply this upper limit in this and lower limit in this. What is the upper limit here? T. So wherever you will have the u, you can simply substitute as a t. So e power minus t sine t plus cos t. Okay, this is for the upper limit value. Next minus. So if you substitute the lower limit value, so if you substitute the lower limit value, e power 0, e power minus e power minus 0, that is e power minus 0 or e power plus 0, whatever it means, value is 1. So it is 1 into sine 0, sine 0 value is 0, plus cos 0, cos 0 value is 1, that is nothing but 0 plus 1, 1 into 0 plus 1, okay, that is nothing but 0 plus 1. So if you simplify this entire equation, okay, what you will get? So if you simplify this one, minus 1 by 2 into e power minus t, okay, into sin t plus cos t, into plus minus 1. So here you will have outside minus term. If you multiply this minus term to internally to hold this equation, then this plus 1 will come first and this entire term will come as a next. There is nothing but interchanging of these two terms, and finally we will get it as a 1 minus 1 by 2 into 1 minus e power minus t into sin t plus cos t. Okay, so this is the way you have to simplify the problem by using the that is division by power of s method. Okay, right. Right. So if you see in this example, okay. So next, this is one more example which will comes under this problem. So Laplace inverse of s square 1 by s square into s square plus 1. So now this should be again divided into two terms, that is 1 by s square into s square plus 1. Okay, now this entire term can be represented as f of s. Now this can be represented as Laplace inverse of f of s by s square. So here we have to take two integrals because it is a square term. So we have to apply the 2 times integration. Okay, we have to apply the 2 times integration. So f of s is nothing but Laplace inverse of f of s is nothing but 1 by s square plus 1. So it is direct equation. It is here a value is 1 by a sine ab. So if you see here, a value is 1 by 1 sine 1 into t, that is nothing but sine t. This is your f of t. Now directly you can use the formula by division by powers of s method. Laplace inverse of 1 by, so here we'll have the s square. So first initially we'll take only one s term. Okay, 1 by s into s square plus 1, that is equal to Laplace inverse of 1 by s into 1 by s square plus 1. Okay, so from that apply that division by powers of s method. So 0 to t f of u into du. Okay, what is f of u here? F of u is nothing but your sin t, that is sin u. Integration 0 to t sin u into du. Okay, right. So apply the integration for sin u. So apply the integration for sin u. Integration sin minus cos u, where the limits there is from 0 to t. So 0 to t. If you take minus outside, so substitute the upper limit in u and also the lower limit in u. You get as a cos t minus cos 0. Cos 0 value is 1. Okay. So you apply this minus sign internally, then these two terms will get interchanged, then you will get 1 minus cos t. So this is your f of t value. Okay, so we'll have the function as 1 by s square into s square plus 1. So we did for only 1 by s into s square plus 1. So now we have to go for s square term. That is nothing but once again we have to apply this division by powers of s method. So we used it for only 1 by s term. So now we are going to apply for 1 by s square. So we did for only one integral. Okay, so this is for only division of s method. Okay, 1 by s method. So if you go for s square, then again we have to do the integration with respect to this f of t function. Okay, so Laplace inverse of 1 by s into 1 by s into s square plus 1. This for this function we did we have converted this f of s into your f of t. Finally we got this 1 minus cos t. Okay, so apply this again one more time of integration, that is integration 0 to t f of u into du. What is f of u here? F of u is nothing but 1 minus cos t. Okay, so integration 0 to t f of u du, that is nothing but 1 minus cos u into d. So if you apply this integration, so integration 0 to t 1 minus cos u. What is integration 1? That is nothing but u. That is integration cos u, sin u. Okay, that is nothing but sin u. So u minus sin u. So limits are 0 to t. Okay, so we'll apply this upper limit. What you will get? T minus sin t. Okay, t minus, wherever you will have the u, you simply substitute as a t. T minus sin t minus, when you will substitute the lower limit, 0 minus sin 0, sin 0, that is nothing but 0. So finally we get t minus sin t only. Okay, right. So this is the way you have to solve the problem by using this division by powers of s method. Okay, so previous the first two methods are related to only in the denominator you will have the s. Okay, that is we did for only one time integration. But in the last example, so we have used the s square term. Okay, so if you use the s square term, then you have to do 2 times integration for this f of t function. Okay, right. So in this class, we have seen the multiplication by powers of s method and division by powers of method, and these are the formulas related. This is your s into f of s formula, and this is the generalized formula for the multiplication by powers of s method, and also for the division by s method, this is the formula, and for nth power, okay, for nth power of s, then this is your generalized formula. Okay, right. So now, so these are the frequently asked questions. So whatever the questions I have given here, so already we did the example problems based on these questions only. Okay, so if you practice that example, then you can easily do these problems. Okay, right. So assignments. Okay. So these are the two questions I have given the assignments. So you can do. Right. So here s square, that is Laplace inverse of s square into f of s. So what you have to do? So this f of s function should be converted into f of t. So it is multiplied by s square. So that's why what we have to do. So we have to do 2 times differentiation for this f of t function. We have to do 2 times differentiation for this f of t function. Okay. And similarly here also Laplace inverse of 1 by s square into 1 by s square minus a square. So this is your f of s. Okay. Laplace inverse of f of s by s square. And the division will have the s square term. So we have to do the 2 times integration 0 to t and integration 0 to t f of u du, because we have the s square term here in the denominator. Okay, in the denominator you will have the s square term. So that's why we have to perform the 2 times integration to the f of u function, f of t function. Okay, right. So these are the standard textbooks you have to refer for this. Laplace transform or inverse Laplace transform or Fourier series, whatever are the differential equations. Okay.